So we want to look at strain, stress, and Young modulus. You see, strain is the ratio of the extension of an elastic material to its original length. That is strain. And stress is the ratio of force to the area of an elastic material. So stress is force over area. And Young modulus is the ratio of stress to strain of an elastic material. Now, like we said, Young modulus is stress over strain. But remember that it's already been stated that stress is force over area and strain is extension over original length. So putting that here, we can first of all say that Young modulus is stress. Rather than say over strain is divided by strain, this is exactly what is here. Now we can say that Young modulus Y is equal to stress, which is force over area, divided by strain extension over original length. Young modulus can now be force over area times original length over extension, and that will be FL0 over AE. So this is another relationship to get Young modulus if we don't want to use this. So that's that about that. It's now important to note that, you see, Hooke's law can also be stated in terms of stress and strain. You see, Hooke's law states that stress is directly proportional to strain. That is, stress is directly proportional to strain. And we can remove this proportionality limit and say stress, this is stress, is equal to Young modulus times strain. Young modulus times strain. So Young modulus is the constant here. So that's that about this. Stop and do it again. Just stop. Graph of stress against strain. And so this is the graph of stress against strain. A is the proportionality limit. E is the elastic limit. C is the yield point or lower yield point. D is the ultimate stress or breaking stress. And E is the fracture point. And so, you see, from here to here is the elastic region. All these are elastic region. From here to here. And so Hooke's law is to obeyed from here to here. And the material still gains the original shape. But from here to here, Hooke's law is not obeyed, but the material regains the original shape. So they install elastic within this point. So that's that about that. The ultimate stress or breaking stress is the maximum stress the object can hold. And point E is the point where the material breaks or snaps. So that's that about the graph of stress against strain. Example 5. This question is on strain, stress, and Young modulus. A wire of length 5 meters. Let's write out what we're given. The length is 5 meters. And the diameter is 0.25 millimeter. So just need to divide that by 1000. And that will give us 0 or 2.5 times 10 raised to power minus 4 meter is extended by 0.25 millimeter. Sorry, the diameter is 2.0 millimeter. That's a mistake. And so this will be 2 times 10 raised to power minus 3 meters. And so the extension is given as 0.25 millimeter. And so we have to convert to meter, and that will be 2.5 times 10 raised to power minus 4 meters. So a wire of length 5 meter and diameter 2.0 millimeter is extended by 0.25 millimeter when a force of 50 Newton, and that's the force, was used to stretch it from its end. Calculate the stress on the wire. To solve this, we just have to say we need to get our area. Well, area is pi r squared, but most often we are given diameter. So we know that, but diameter is equal to radius is diameter over 2. If you put that here, your area becomes pi. In place of r, you put diameter over 2, and then square this, pi r squared. This will give you pi d squared over 4. And this is what we'll be using to calculate our area if diameter is given. Otherwise, except when radius is given, then we used radius. Pi times our diameter is given as 2 times 10 raised to the power minus 3 squared over 4. Times 2 times 10 raised to the power minus 3 divided by 4. This is 3.14 times 10 raised to the power minus 6 meters squared. This is our area. Now, let's look for the stress. Stress is force over area. The force we are given as 50 Newton in the question, and the radius, the area is 3.14 times 10 raised to the power minus 6. This is given as 1.59 times 10 raised to the power 7 Newton per meter square. So this is the stress. Now let's calculate the next one, the strain. Strain is the extension of original length. The extension is given as 2.5 times 10 raised to the power minus 4 divided by the original length of the wire is 5. And so this will be equal to, the strain is equal to 5 times 10 raised to the power minus 5. No units. The strain has no units. Then lastly, number 3, Young modulus. The Young modulus is stress over strain. So the stress is given as 1.59. We've gotten that times 10 raised to the power 7 divided by the strain is obtained as 5 times 10 raised to the power minus 5. And so let's get this now. We have 1.59 times 10 raised to the power 7 divided by 5 times 10 raised to the power minus 5. So this is giving us 3.18 times 10 raised to the power 11 Newton per meter square. So this is the Young modulus. You know, we can solve with this formula also, or we say Young modulus is equal to F L naught over AE. So I believe if we do this, we get the same answer. 5, 50 is the force, and L naught initial length is 5 over the area, which is 3.14 times 10 raised to the power minus 6, then times the extension, which is 2.5 times 10 raised to the power minus 4. So that's that about that. If we do this, we are going to have so that's that for this question. A wire of mass 11 kg is suspended from a rigid support by aluminum wire of length 2.0 meter and diameter 2.0 millimeter. Calculate the extension of the wire. We are given the Young modulus as 7 times 10 raised by 11 Newton per meter square, and we are given acceleration to gravity as 10 meter per second square, and then pi, a constant, 3.142. So let's bring out what we are given here. First and foremost, we are given the weight or the mass as 11 kg, 11.0 kg. And so weight is mg. Our g is given as 10 here. So that will be 11 times 10, which is 110. This also serves as the force. The weight is the force in this case. Next, we are given the original length, 2.0 meter. Again, we are given the diameter, which is 2.0 millimeter. And so, converting to meter, that will be 2 times 10 raised to the power minus 3 meter. So the first and foremost we want to do here is to calculate our area. Area is pi d square over 4, which is 3.142 times 2 times 10 raised to the power minus 3, which is the d squared, over 4. So this will give us that the area is equal to 3.142 times 10 raised to the power minus 6 meters squared. Now, let's get our extension. That's what the question says we should get. And we know that our Young modulus is F L naught over AE, where E is the extension. So upon cross multiplying this now, we get that YAE, Young modulus times area times extension, is equal to F force times original length. Now, dividing both sides by Y and A, dividing here by Y and A, we'll get the extension is force times original length over Young modulus times area. Now, what's the force? The force in this question is the weight, which is 110, times what is the original length, which is 2, over what's our Young modulus? Our Young modulus is given as 7 times 10 raised to the power 11, times our area is given as 3.142 times 10 raised to the power minus 6. So let's evaluate this now. So this is giving us 1 times 10 raised to the power minus 4 meters. So that's the extension, or this can be 0.1 millimeter. That's the extension of this wire. Work done on a stretched spring. When a spring is stretched by an extension, let's say E, work is done on that spring, and the work done is given as average force times extension. Now we can say that work done is equal to, initially there's no force on that spring, so the force is 0, plus Meaning when it was not stretched, no force, that's 0. When it's now stretched by a force F, the addition of these two divided by 2 is what we call the average force. Average force times the extension E. So eventually we can say that work done W is giving us half Fe. This is the formula for the extension by the work done by an extended spring or a stretched spring. Also, we know that force from Hooke's law is equal to Ke. If we substitute this into this first equation, I call this equation 1, we are going to have the work done to be equal to half multiplied, in place of F now put Ke, then times the E. This will be half Ke squared. This is the second relationship. Or from the first relationship, since we said F is equal to Ke, we can say that E is equal to F over K, meaning making E inside a formula in this formula. At the end of the day, if we substitute this for E in this first equation, we're going to have W to be equal to half F times F over K. And that will give us half F squared over K. All of this can be used, this is equation 3, can be used to get the work done by a stretched spring. Example 1. If a load of mass 10 Newton stretches a cord by 1.2 cm, what is the total work done? Here, we have that the force is given to be 10 Newton, that's what we are given. And again, we are given the extension to be 1.2 cm. But mind you, we have to convert to meter, divided by 100. This is going to give us 0.012 meters. Now, work done is giving us average force times extension. And that will be giving us 1/2 times the force 10 times the extension 0.12 cm meter, sorry. So that will give us 0.012, please, my pardon. 0.06 joules. That's the work done. Elastic potential energy. You see, when an elastic material is stretched or compressed, energy is stored in that elastic material, and the energy stored is known as elastic potential energy, and it is denoted by the letter W, and it's giving us half Fe or half Ke squared or F squared over 2K. It has exact same relationship or formula as that of work done by an elastic material. So let's take this example. Example 1. A spring of force constant 1500 Newton is acted upon by a constant force of 75 Newton. Calculate the potential energy stored in the spring. For this question, we are given that K is equal to 1500 Newton per meter and force of 75 Newton. Calculate the potential energy stored in the spring. So W is giving us half or F squared over 2K. I'm using this relationship because that's what we are given. So this is the best relationship to use. Our F is giving us 75 squared over 2 times 1500. And that will give us 1.875 joules.